All right, guys, we are going to learn more about molarity and molality and some definition or some dilutions today. So let's pick up in our notes where we left off last time. So I did not do all the different examples for molality or molarity. So we're going to start off with our last example of molarity. Now, if you remember, molarity is, by definition, molarity is number of moles of solute divided by liters of solution. So it's a moles over volume type of calculation. So let's do example 8. I want to know how many grams of sodium iodide are needed to make 500 milliliters of a 0.1 molar solution. So I need to start with the volume here, okay? So I'm going to start with our volume of 500 milliliters. So if I have 500 milliliters, and I should put that extra zero there for sig figs, thing is, molarity is in liters, and this is in milliliters. So I want to get to liters. So how many milliliters are there in a liter? Do you guys remember? There's 1,000. So 1,000 milliliters will be in 1 liter. So that gets me to liters. And then can I use this concentration? I've got a concentration of 0.1 moles of sodium iodide in 1 liter of solution. I can use this concentration that I've made over here to cancel out my liters. So if I put liters on the bottom, so in 1 liter of that solution, I am supposed to have 0.1 moles of sodium iodide. Okay? So my milliliters have now canceled, my liters have now canceled, and I now just have moles. Can I convert moles to grams? Yeah, I can. So in 1 mole of sodium iodide, I need to figure out my molar mass. So if I look at my molar mass of sodium, sodium is 22.99. So I'm going to add that up with 126.90. So let's make a note of this. 22.99 for my sodium and 120, oops, let's erase that. And 126.90 for my iodide. We're going to add that up together. And when we add that up together, let's see, 9, 18, carry the 1, it's going to be 9, 4, and 1. So I will have 149.89 grams per mole here. So I'm going to put that 149.89 grams of sodium iodide. Okay? So mathematically, we're going to take 500, divide it by 1,000, and multiply it by 0.1. So 500 multiplied by 0.1 divided by 1,000, and we're going to multiply by 149.89. So with, let's see, we've got 4 sig figs here, we got 3 sig figs here, so we can really only do 3 sig figs. My calculator spits out 7.4945 right here. So let's see. With 3 sig figs, 1, 2, 3, that 4 tells me to leave it. So I would report this as 7.49 grams of sodium iodide is what I'm going to need. Okay? All right, so 7.49 grams. So notice we're using our concentration to cancel out units. So a lot of these concentration problems are, how can you use your units to get to the units that you want? Okay, let's do molality now. Molality is moles of solute per kilogram of solvent. So how many grams of acetic acid are needed to make a 0.5 molal solution in 750 grams of water? So the thing that we want to start off with here is we want to look at starting off with our grams of water. So I have 750 grams of water. And if we look at molality, it's per kilogram of solvent. Hopefully you agree that water here is our solvent and the acetic acid here is our solute, right? So I need to get my 100 or 750 grams of water into kilograms, right? So I have 1,000 grams of water in 1 kilogram of water. Okay, so my grams of water cancel out. I do have kilograms. Now, remember using our concentration to use the units to cancel things out? What does this molal concentration tell us? It tells us that we have 0.50 moles of acetic acid in 1 kilogram of water. That's what that means. Okay, so I can use this relationship to cancel out the kilograms that I have. I need to put the kilograms on the opposite side, so it's going to go on the bottom. So in 1 kilogram of water, I'm going to have 0.5 moles of acetic acid. Okay, so my kilograms of water cancel out and I have moles. Now the next thing I need to do is just convert moles of acetic acid to grams. So I need to get my molar mass of acetic acid. So in 1 mole of acetic acid, I have how many grams of acetic acid? So we need to add up, let's see, we've got 4 total hydrogens. So hydrogens is 4 times 1.01. So if I look at my periodic table, hydrogen is 1.01, carbon's 12.01, and oxygen is 16. Okay, so we're going to use those masses. So we've got 4 hydrogens. We've got 2 carbons in acetic acid, so 2 times 12.01, and we've got 2 oxygens. We're going to add all of that up. So 4.04 plus 24.02 plus 32 gives us a molar mass of 60.06 grams per mole. Okay, so we need that grams here on top, so 60.06 grams. Okay, so mathematically, we're going to take 750, we're going to divide it by 1,000, and then we are going to multiply it by 0.5 in the next step, and then we're going to multiply it by 60.06. So when we do that, our calculator spits out, oh, I don't want that there. Our calculator spits out 22.5225 grams. Now we only have 2 sig figs here. Remember that 0 at the end is just a placeholder because there's no decimal there. So that 5 is going to tell us to round up. So we're going to have 23 grams of acetic acid. that we're going to need to get to make that solution. Okay, example 13. What is the molality of a solution that is 31% potassium iodide by weight? Okay, so there are a couple things that we've got to do here. One, we've got to figure out the formula for potassium iodide. So if I look at my periodic table, potassium is in the first column, so it's going to have a +1 charge. And iodide is in the second to last column, the halogens, so it's going to have a -1 charge. So if potassium is a +1 and iodine is a -1, I'm going to need one of each to create potassium iodide. So the formula for potassium iodide is just Ki. Okay. Now the next thing we're going to have to do is we're definitely going to need the molar mass, right? So potassium, if we look on our periodic table again, potassium has a mass of 39.10 to the 10th, and iodide has a mass of 126.90. So we're going to use those masses. So potassium is 39.10 and iodide is 126.90. So we're going to add that up. So let's see, 6 and add that, 6 and 1. So we'll get a molar mass of 166.0. Okay. So the other thing that we've got to do is we've got to think what this 31% means. If I have 100 grams of this solution, how many of those grams are going to be potassium iodide? What's 31% of 1,000? So 31% of 1,000 is 310 grams. So I'm going to have 310 grams of potassium iodide. All the rest of those 1,000 grams is going to be water, right? So 1,000 minus 310 grams, that is my water in grams, right? Okay, so if I want to do that, that's really going to be 690 grams of water if I want to simplify that. Okay, we can think of it as 690. Okay, now molality is moles per kilogram. So I need to get my moles on the top, the potassium iodide I need to get those grams into moles. So I can do that using my molar mass. So in 166.00 grams of potassium iodide, right? 9 point. I have 1 mole of potassium iodide. Okay, so my grams of potassium iodide cancel, and I now just have moles of potassium iodide, which is what I want. And then the next thing, I need to get the grams of water into kilograms. So I have 1,000 grams of water, and yay, it is now wanting to think. 1,000 grams of water will give me 1 kilogram of water. So when it will let me write again, we'll put a kilogram of water on the bottom. So water and 1 kilogram of water. Okay, so if we do that, we are going to have our grams of water cancel out. So our units that are left are moles divided by kilograms, which is exactly what we want for molality. So we're going to take 310 and we will divide it by 690. Then in the next step, we are going to divide by 166. And then in the next step, we are going to multiply by 1,000. So when that is all said and done, let's see. We're going to pretend that we have 2 sig figs. We will have 2.7 molar potassium iodide, or you could also write this as 2.7 moles of potassium iodide per kilogram of water. Both of these mean the same thing. Okay, so there's a couple more practices of how you do calculations with molarity, moles per liter, and molality, moles per kilogram. All right, next thing, we are going to look at the definitions of some of the things that we've been working with. So percent mass is the mass of the solute divided by the mass of the solution times 100. Okay, so there's the definition of percent mass. I can't speak. Molarity, big capital M here, is number of moles of solute divided by liters of solution. Okay, mole fraction is the amount of moles of whatever you're measuring. It's usually solute, but not always, divided by total number of moles. Or you could also have moles of solvent divided by the total number of moles. And then molality, little m, lowercase m, is equal to the number of moles of solute divided by kilogram of solvent. Okay, so those are the 4 main ways that we do concentration measurements in chemistry. In chemistry, the biggest one, the one that we use the most, is molarity. Molarity is used all the time in chemistry. Acids and bases are based on molarity. pHs are based on molarity. And when I make up concentrations of solutions or whatever, I always calculate them out in terms of molarity. Okay. If you get into AP Chem and you get into the Nernst equation or any of those, it's all based on molarity. Okay, so it's a concept that you're really going to want to know how to manipulate and how to use. Okay, so we're going to talk about dilution. Lots of times when I am in the chemistry lab, I will have a stock of some kind of solution and I need to dilute it into something that is a little bit weaker. Okay, so this is called Smith's magic rule of dilution, and this is in honor of Mr. Smith, who was the first chemistry teacher at Cottonwood High School. So he's taught all of us through the line of all the chemistry teachers that I have been mentored by. And so we named this after him. So he was the originator of this. So let me just do a thought experiment for you. How many of you guys have made juice from concentrate? If you've made juice from concentrate, you've seen these frozen cans. And when you make juice from concentrate, we're going to say that this can has the juice of 10 oranges in it. Okay, I want to make this juice. So I grab the pitcher, right? And I put this can in of the concentrate. And then I have to put 3 cans of water in there. And I stir it up, right? I start with the orange concentrate and then I add the water. Let's get a blue pen. And I add the water and then I mix it all up. And once it's all mixed, I have orange juice. Okay, now I started out with this can with the juice of 10 oranges. How many oranges do I have in here? after I put in 3 cans of the water. Don't I still have the juice of 10 oranges? I just diluted it with water. So the thing that we are going to analogize this with is the number of moles that you had at the beginning of the dilution. So at the beginning is equal to the number of moles of whatever solute that you have at the end of the dilution. Okay? So moles in is going to equal number of moles out. The number of moles doesn't change. It's just the concentration changes. Okay? So here it is stated again. The number of moles of solute before the dilution equals the number of moles after the dilution, or at the end of the dilution. So here is our dilution equation. M1 is moles at the beginning, or moles at the initial, multiplied by the volume 1, the volume at the beginning, is going to be equal to M2, number of moles at the end, let me rephrase that. Sorry, not number of moles. Capital M is molarity, not number of moles. So molarity. So molarity of 1, which is moles per liter, right, times our volume, and this is going to be 1, is going to be equal to moles per liter, or the molarity of our dilution, times our volume 2. Okay? Now, volume is always in liters, is it not? So if I have liters like this, that's going to be canceling out, and liters, this will be canceling out. So moles is equal to moles, just like I still have 10 oranges in here. The number of moles that I begin with is going to be equal to the number of moles that I end with. Okay, so here is an example here of how to use this. How many milliliters of a 12 molar solution of hydrochloric acid is needed to make 250 moles or mils of a 2.5 molar solution? So what we have to decide is, what is our volume 1, our molarity 1, our volume 2, and our molarity 2. So let's go in and label these things. So our 12 molar hydrochloric acid solution, that is definitely molarity 1. Needed to make, so that is what we want to end up with. So this is my volume 2, and a 2.5 molar solution, that is my molarity 2. So what I'm trying to find then is how many mils. So I'm trying to find V1. Excuse me. That is my thing that I'm trying to find. So I'm going to set this up. Now, you'll notice that if I do the units on this, as long as the volume units are the same on both sides, I can just use whatever volume units I want, because they're really going to cancel. Okay, so if I have mils, I can use mils on both sides. Even English systems, if I have cups on one side and cups on the other side, or teaspoons or tablespoons on both sides, I can use those units because they will cancel out. So there's really no need, because I'm looking at mils and I have mils here. There's no need to change those milliliters from milliliters to liters. Absolutely no need whatsoever. Okay, so hopefully Word will let me write here. So we're going to set up our equation. So volume 1 is the unit that we want to figure out. Our molarity 1 is 12.0. I'm not even really going to pay attention to units here. I know I'm breaking all kinds of rules. 250 mils is our volume 2, and our concentration 2 is 202.50. So I just really need to isolate V1. So I'm going to take 250 multiplied by 2.50 and divide it by 12. And I get 52.083 repeating. So 52.083 repeating. Now, we need to remember that the volume that we are doing is in milliliters because that is the volume that we have put in here. We only have 3 sig figs, so 1, 2, 3. That 8 tells us to round up. So we're going to report this as 52.1 milliliters of that 12 molar HCl is what we are, hydrochloric acid is what we are going to need to start with. So 52.1 mils are what we're going to have to start with. Now, in order to just show you how this would work in the lab, if I wanted to actually make this solution, what I would want to do is I would want to put a little bit of water in here, just a little bit. And then I would want to measure out the 52.1 mils of the hydrochloric acid and put that acid in. So that would be the acid layer. And then I would want to add more water until I hit the 250 milliliter mark. And usually our volumetric flasks have a line here. So I'd want to fill that up until I hit that mark. And I'd want to stir while I'm doing that. Now the reason I want to put the acid in a little bit of water first is acid, when we add it to water, generates a lot of heat. So I want to have a little bit of water in there already to absorb the heat as I'm making this and I'm mixing this. Okay, so that is how you make a dilution. Okay, you add a little bit of water and then put a little bit of, then put whatever you're wanting to put in there, and then add more water until you get to the volume that you want. Okay, so let's calculate number 13. Calculate the molarity of a solution when 30 mils of a 2 molar solution of sodium sulfate is diluted to a volume of 150. So let's figure out. We've got B1. This is our molarity 1, and this is our V2. So we're calculating our molarity. So we're calculating molarity 2. So V1 times M1, so 30 mils times 2.0 is equal to my M2 times 150. Okay, wow, wonder why that line is there. Okay, so 30 times 2, which is 60, divided by 150 will give us a molarity of our diluted solution of 0.40 molar. So that's going to be our solution. So we will have 0.4. Why is it doing that? We will have 0.4 molar solution of sodium sulfate. for our dilution. Okay, review. We want to just do a little bit of review on some of our molarity and molality. So let's just do a couple of these. What is the percent concentration volume, so of 20 mils of acetone in 65 mils of ethanol? Remember, percent concentration is the part that we want the solute divided by the total. Okay, so our solute is 20 mils of acetone. So we have 20 mils of acetone, but our whole solution is our 20 mils of acetone plus the 65 mils of ethanol. So we're going to have 20 divided by 85. So 20 divided by 85, and we need to multiply it by 100 to get a percent, right? So 20 divided by 85 times 100 will give us 23.5. Let's see, we've got 3 sig figs here. We have 23.5% acetone. Okay, how'd you do with that? All right, let's do number 4. What's the molarity of a solution formed by dissolving 18 grams of sodium nitrate? So the first thing we've got to do is find the formula for sodium nitrate. So sodium is a +1, and if you look on your polyatomic sheet, nitrate is NO3 -1. So we're going to need one of each. So sodium nitrate, we are also going to need to figure out the molar mass. So sodium is 22.99 when we look at our periodic table. Nitrogen is 14.01. And we've got one of them, so 14.01. And we've got 3 oxygens, so 3 times 16. We're going to add all of that up together. So 22.99 plus 14.01 plus 48. 3 times 16 is 48. We're going to get a molar mass of 85 grams per mole. Okay, so here we go. I think we've got our background of what we need to do. So we're going to take our volume first. Well, actually, we can take our volume first, or we could take the grams. It really doesn't matter, either way. So let's take our grams first. We've got 18 grams of sodium nitrate, and we're trying to get moles per liter, right? So I need to get sodium nitrate into moles. So we did our molar mass, 85 grams of sodium nitrate gives us 1 mole of sodium nitrate. So our grams cancel out, and we do have moles. So we do have moles on top, which is what we need. Now we need a volume on the bottom. We are given a volume of 250 milliliters, but we don't want mils on the bottom. We want liters. So I have 1,000 milliliters in 1 liter. So my milliliters cancel out, and now I do have moles per liter. So mathematically, we are going to take 18, we're going to divide it by 85, and we are going to divide it by 250, and then we are going to multiply it by 1,000. We've got 3 sig figs on this, so this will give us 0.847. Okay, so 0.847 molar sodium nitrate, when this will let me actually write. Okay, 0.847 molar sodium nitrate. Okay, so there's a practice of a molarity. Let's do a molality problem. So let's do number 9. What is the molality of a solution formed by dissolving 15 grams of glucose in 600 grams of water? So molality, we're trying to get moles of the solute divided by kilograms of the solvent. So hopefully you remember that the glucose is going to be the solute and the water is going to be the solvent. Okay, so we need to get the 15 grams of glucose in 2 moles. So 15 grams of glucose, which is C6H12O6, and I already have the molar mass here, so I have 180.18 grams of C6H12O6 for 1 mole of glucose. So my grams cancel out. I'm into moles. So I have moles on top like I want, right? Now, I do have grams of water. I have 600 grams of water, but I don't want grams, I want kilograms. So I have 1,000 grams of water in 1 kilogram of water. So my grams cancel out, and I'm left with kilograms. So I have moles per kilogram. So we're going to take 15, we're going to divide it by 180.18, and then we are going to divide by 600, and then multiply by 1,000. So the molality, then, let's see, we got 3 sig figs. This will come out to 0.139 with our sig figs. Lowercase molal glucose, C6H12O6 in water. Okay, so there you go. There's some more examples of molarity, molality, and some mass percent, and also how to use dilutions. Okay, so next time we are going to be practicing that some more. And then we are going to also start looking at solubilities of different ionic compounds in water. All right, have a great day. We'll talk to you later. Bye.